What is going on, guys? My name is Amos and I'm back again with another video. So in this particular video, I'm going to be sharing with you guys a hobby project that I've been working on for the last couple of weeks. I think 3 weeks now. I'm going to share with you guys my motivation for working on this particular hobby project, as well as what I hope to achieve as we develop this particular piece of software into something that other people can use. So the project or the hobby project that I'm working on is known as Fintom. So Fintom means finite automata. And as we can see from this particular description, it is a lightweight C++ library for working with finite automata. And we're basically talking about manipulating DFAs or deterministic finite automata, NFAs or non-deterministic finite automata. And we'll also look at how we can convert regular expressions into NFAs and NFAs into DFAs, and maybe look at how we can minimize DFAs using, of course, C and C++. But this library is going to be entirely written in C, but then you can also use it in C++. So in the beginning, we'll first of all make sure that the C stuff is working and it's working without any problems or with minimal problems before we can see how we can see how the functions or the functionalities that we're building into this libraries also work in C++, because there are a few tweaks that we have to apply here and there. So description has already been given. So what is my motivation for working on this particular hobby project? So I'm someone who likes mathematics and also the theory that is behind how computers work, how compilers work, and how computers understand natural language and all that good stuff. So it was actually one of my favorite, I think, courses or modules last year. And I'm currently a student. I'm currently in my 4th year at the National School of Applied Sciences in Tetuan, and we had this particular course or module in our 3rd year. I'm currently in my 4th year, so it was one of my favorite modules, and I just want to see how I can apply my programming knowledge, my programming skills, and my C knowledge, and come up with something that is concrete, or a software that can be used, a piece of software that can be used for simulating finite automata or the theory of computation. So as a whole, so it's going to be a very, very big project. So we actually worked on a similar project last year. We actually worked on a similar project, but then it only covered, I think, DFAs and NFAs. So I actually want to see how I can extend this to simulate PDAs and also Turing machines and all that good stuff, and also see how we can throw in some compiler theory here and there, so that we can simulate all that good stuff. This is actually going to have. I'm also working on the application or the desktop the desktop or the application version that is going to heavily rely on this particular library, but then you can you visualize what is happening and all that good stuff. So I think the project, let me see if we can bring it up here. So we have GitHub, I think, Amos Nurenda 123. So I've actually forgotten what did I call the project? So I've actually forgotten the name. Okay. It's actually this particular so this is going to be the desktop application that heavily relies on the Fintom library. So this is actually going to be built with Raylib, because I've worked on a few games And I actually like Raylib a lot. And we also use a companion library, which is RayGUI, which is a header-only library, and that relies on Raylib, of course. And Raylib, we're going to use Raylib for the rendering and all that good stuff. And RayGUI has some widgets and also some containers that we can sort of like use in our project. Things like horizontal containers, vertical containers, and all that good stuff. And if there's anything that will be missing, we'll see how we can sort of like create that on our own, because there's a tool that we can use to create containers. I think RayGUI containers, just to sort of like generalize my description. So this is everything. I'm just starting with this, so I've not gone very far. Basically just, this is just, basic project setup and all that good stuff. You have like the CMake file, and then here you can see that we depend on Raylib and RayGUI. So what I'm doing with Fintom, the library that we're going to that has the logic and the functionality. What I'm doing with this is I want to make sure that I only depend on the we have like zero dependencies on external tools and external libraries and external software. So we just want to make sure that we implement everything on our own. And I also like want to sort of like I've built a few things in the C programming language, but I want to take my programming skills to the next level. So I want to see how I can sort of like apply my what I already know, and sort of like also gain more experience and more knowledge of the things that I don't know at the moment. And that's the reason why I'm like sort of like trying to avoid dependencies and external, depending on external libraries. Like there are like libraries we can use for processing JSON, serialization, and all that good stuff. But I want to like try to see how I can do that on my own. So let me first of all open my Visual Studio Code so that I show you what I have at the moment, what is working and what is not working. So the idea here is to sort of like let me just show you the current interface, the interface that we are using. So let me just close that. So this is an example that I was working on. So after creating the basic structure of the automata or of the automaton, either DFA or NFA, this is how you can sort of like build everything in a sort of like step-by-step fashion. You like build the automaton, then you create the alphabet, and then you create the states. And then after creating the states, you create the transitions. After creating the transitions, and you sort of like generate you generate the corresponding dot file, and then you can also generate the corresponding JSON file, and then you can also like print the information. You can also print the metadata about the metadata about this particular automaton, and many things that you can do. You can print the transition matrix and all that good stuff. So the idea is to be able to what we'll get as output is of course going to be either a dot file or a JSON file, and we can sort of like copy this particular code and sort of like paste it into Graphies, for example, and Graphies will sort of like render and generate the image that corresponds to this particular textual data that we have here. So let me just show you an example of, so this is what we are sort of like, this is what we're getting as output. This is what we're getting as output, let's go back to, of course, we've opened a lot of windows. Let's see. Yep. So if we like look at I think it's the Graphies online, the Graphies online editor, like so, has to be this one. So you can see that if we paste the the textual representation of the automata, So we sort of like generate this particular image, that this particular automaton with all the states and all the transitions. So the starting states are going to have this I would say pale yellow color or something like that. And then the ending states or the accepting states are going to have like this, double secular representation, right? So here Q0, for example, is both a starting and accepting state. It's a starting state because it has this pale yellowish color, and then it's an accepting state because it has this double secular form, right? And for example, Q2 is not a starting state. It is an accepting state because it has this double secular form that we have here. Q0 has a loop. Q3 also has a loop, and then we can see the different transitions and the remaining states, and we get some basic description here. Like the number of states that we have and the size of the alphabet. In this particular case, the alphabet has 4 symbols, that is A, B, C, D, and E. And you can see what I'm trying to do. Now, what we can do is we can maybe directly generate this particular image from with our Fintom library. But then we would actually have to like depend on external tools to be able to achieve that. So to avoid all that, and as I'm trying to like process everything and sort of like see how the project is coming up and all that good stuff, maybe we might do that in later on, as we maybe recognize the importance of like adding such features to our library. But for now, generating JSON or dot files is going to be sufficient for what we actually want to do. So the library is going to spit out this textual representation of the dot file, and then we can use external dot file visualizing tools like Graphies, for example, to generate the corresponding image. And then if we want here, we can sort of like download the image. We can download the PNG, the SVG, and many other formats that are represented here. So we also have the JSON representation of the same information. So if you have like maybe let's say a web visualizer or something like that reads the JSON data and maybe generates the image from the JSON data. So that's why you like need this particular file. So it contains the same information as this particular dot file that we have here. So we have all the states, all the transitions, and the alphabet, the metadata, like the alphabet size, the state count, and the type of a machine that we're talking about. So here we have like it's going to be a finite automaton. So we also have like a few statistics, like the average transitions per state. So this would be like the density of the automaton. So at average we have 2 transitions per state, and then we have like the total number of transitions, the total number of accepting states, and then the total number of starting states. And this is we can actually see this here, that we can actually see that we have 3 accepting states and 2 I would say starting states. So this is what we are generating at the end. So I was trying to come up with a very clean, API, like all the public functions, all the public library functions have been prefixed with the FA, the FA, I would say prefix. So we have like FA, like state. So now we know that we are dealing with states. So we are talking about state creation, state finding a state, and destroying a state. Many of these good and very, very useful functions. And for example, for creating an automaton, we have like FA auto create. So that is what we have here. So let me first of all show you how everything is going to be represented in memory. So how everything is going to be represented in memory. So we have one very big header file. So I'm trying to sort of like decompose this header file into multiple header files. So at the moment I have like FA, but I'm trying to create the FA operation that is going to store all the that is going to have all the operations we can perform on Automata, such as taking the union, taking the concatenating Automata, and also taking the intersection, minimizing Automata, and generating Automata from regular expressions and all that good stuff. So this is where all the operations are going to like go. Right now, all the operations are in the FA header, but it's like very, very big, and it's going to be very hard to like skim through and find out what functions we have in the header file. And so it's going to be very hard to like maintain with all this documentation that we have here. So we might have to like do some more decomposition. So as for the structures, so here are the structures that we are using to like store the information that we are storing about the automaton. So what we have here is as our first state here as our first what we have as our first structure is the FA state. So the FA state is going to be storing information about a particular state of the automaton. So we're going to store like the label, which is the textual representation of the state. So as we can see from this particular image, the textual representation of the state of this particular state here is Q0. The textual representation of this state here is Q1. The textual representation of this state is Q2, so on and so forth. So we actually store the label or the textual representation of that particular state. And then we have a Boolean that tells us whether this state is a starting state. We also have another Boolean that tells us whether a state is an accepting state. And then we also store a pointer to the head of the linked list of the singly linked list of transitions where the current state where the current state is the source, right? So that sounds a little bit confusing, but what I mean here is let's say we have a state, we have a state S, right? We have a state S. So S, so we're going to have a label S, and if S is a starting state, this Boolean is going to be, this value is start is going to be true. If S is an accepting state, this value is accept is going to be true. And then now this particular pointer is a pointer to the singly linked list, of transitions where S is the source, right? Where S is the source, right? So in this case, let's look at the image that we have here, so that will help us understand what is happening here. So let's look at, for example, let's look at Q0 here. Let's look at Q0. So Q0 is a state, and what the trans pointer represents is actually it's going to point to the head of this is going to point to the head of the singly linked list of transitions. So for example, let's look at the transitions where Q0 is the source. So we have the transition where the symbol is E, the transition where the symbol is B, and the transition where the symbol is C, and also the loop here, the transition where the symbol is A. So in these four transitions, Q0 is the source. So all these transitions are going to be stored in a singly linked list, right? All these transitions are going to be stored in a singly linked list. Now that singly linked list is going to have a head. Now the head is going to be our starting point. It's how we can sort of like, it's how we can loop through all the different transitions that a particular state has. So that's why the pointer is very, very important. So if we point to the head, we point to the head of the singly linked list of transitions, we'll be able to sort of like loop through all the transitions that we have here. And that is what we have here. That's the concrete information that we have here. And then entrance, this is like the number of outgoing transitions. Remember that we can have incoming transitions and outgoing transitions. So let me just go back to the image so that we understand what we're talking about here. So here Q0 only has, outgoing transitions. The transition with the symbol A is an outgoing transition. It's a loop, so it's a loop, so it goes from Q0 to Q0. So this is an outgoing transition. You would look at it as an outgoing transition. If you're looking at the first, the first Q0, and if you're looking at the second Q0, you would sort of like, consider it as, an incoming transition or something like that. The transition with the symbol E here is an outgoing transition. So same applies to B and C. The transition, so from Q3 to Q2, if we look at it from, Q2's point of view, this transition with the symbol E is an incoming transition. But what we are sort of like interested in, what we're worried about here is the outgoing transition, right? The outgoing transitions. So we have a count for the total number of outgoing transitions from a particular state, right? Great stuff. So this is what the state structure is representing. So we'll actually add more fields if we find that we need more fields to like store more information and to sort of like make it easier to use this particular library, right? We'll talk about this a little later, but then another important structure is going to be the transition structure. So we also have to like store information about a particular transition. We need to know what is the source, what is the destination, what symbol are we consuming, and what is the next transition in the singly linked list of transition. What is the next transition? So a pointer to the next item. So this is what we have here. So the symbol is the symbol we are consuming. Now both the symbol and the label here are going to be dynamically allocated. We're going to allocate them on the heap and not on the stack. So that is the idea. So here we have, for the transition, we have the destination, the source, and then the next pointer, or a pointer to the next item, to the next transition in the singly linked list of transitions. Now I'm saying all this because I'm assuming that you guys, have some basic knowledge of, data structures, especially in C as a programming language, how linked lists are implemented, how hash tables are implemented, how sets are implemented, how trees are implemented. So this particular library heavily relies on these powerful and important data structures. So my assumption is that you guys are familiar with ideas on have knowledge, or have at least looked at how a singly linked list is implemented, a doubly linked list is implemented, and also a secular linked list and the tree data structures, and many other important data structures that we're going to discuss. But then these are like the basic data structure. So everything else can is just like a complex representation or a complex data structure that utilizes linked lists, trees, and things like that. So that is the basic idea. And then finally we have the auto structure. The auto structure. So the auto structure is going to be it's going to be our automata structure, our automaton structure, right? Great stuff. So this is going to have, we have n states. So this is a count for the number of states that the automaton has. And then we also have a pointer to the alphabet. So this is dynamically allocated, right? This is going to be dynamically allocated, I think. Yeah. So this is a pointer to the alphabet. It's a pointer to the alphabet of this particular automaton, right? And the alphabet is implemented as a set. Now, why implementing it as a set? Because, later on we'll talk about how we can take the union of automata, how we can take the intersection of automata and many of those interesting operations, and we'll sort of like have to, if we talk about the alphabet, for example, when we find the union, the alphabet is going to become bigger, right? The alphabet is going to become bigger. So we might have to take the union of, the alphabet of automaton A and then the alphabet of automaton B to find the new alphabet and things like that, right? So we might have to do that. And that is implemented as a set. And then the set actually has all those beautiful and all those powerful and nice operations that we can apply on sets: union, intersection, difference, and many other operations that we can apply on sets. And then we also have a pointer to an array of state pointers. Okay, that sounds a little bit confusing. So, but what we are doing here is we'll first of all create. Let's see if we have our main. We can find our main. So what we're doing here is, if you look at what we have here, for example, where we're creating the states. So this is where we're creating the states. So f state create returns a pointer to the created state. And then when we put these pointers, we'll then put these, state pointers into an array that we are calling states. Right, into an array that we are calling states, right? Into an array that we are calling states. So the states array is an array of pointers. The states array is an array of pointers to states, right? To individual states, right? Is an array of pointers to individual states. So that's the, that's what we have here. And yeah, so this is all the, this is all the, yeah. Oh, we also have the stack. Now the stack is a data structure. Is a data structure, right? I'm also going to assume that you guys know what a stack is. So a stack is going to store, like a stack of books. This is going to store automata. So we'll have like a stack of automata. So what we're going to do with this stack is that this stack is going to help us with maybe taking the union of n automata, taking the union of taking the intersection of n automata, and also maybe using the using Thomson's construction to come up with an automata, from a regular expression. We're going to heavily rely on this stack to build, the automaton, the resulting automaton in sort of like a step-by-step fashion. So by, popping and pushing to the stack and applying the corresponding, applying the necessary operation, we'll be able to get the result. We'll be able to get the desired result. And we'll actually look at how, this is going to be implemented and how we're going to use stacks a little bit later. And for now, these are the structures that I'm using, but then I might add to this particular structure, right? So yeah, so this is what we have. And now I told you that the alphabet is going to be implemented as a set. Now here are the operations that we can apply on sets. So we have a set create function, and then shortcut functions to create a string, a set of strings, a set of integers, and cleaning up, destroying, clearing the set, inserting into a set, removing items from a set, checking whether an item belongs to is in a particular set, getting some statistics, the size of the set, is the set empty, taking the union, intersection, and many of those operations. So these are the operations that we have here. So all of them have their implementation in the set.c file, right? So we'll actually look at this a little bit later. Then another structure that I have here is going to be is the hash table, right? Is the hash table. Now the hash table is a very important data structure. And if you've looked at data structures, one thing that we always talk about is the complexity. Yeah, the complexity of the structure that we have. So how costly is an insertion? How costly is lookup? So how costly is reading from that particular data structure? So that is what the complexity, tells us. A hash table is a very important data structure in the sense that, lookup is like very, very fast. Lookup is very, very fast. Writing into this particular structure might be a bit slow compared to the lookup because we have to do the hashing and things like that, and we have to go through all that, process. And it might actually take, a few, maybe a few seconds or a few minutes, right? Compared to the lookup and all that thing. So, but then the lookup is going to be accelerated because the lookup is going to be done in constant time. So that is why this particular structure is very, very important. Now, this is just, a summary of what a hash table is. Of course, there's more to that, but then this is like, the global picture that we have of why we use these hash tables. So why I use these hash tables is in my minimization function, I think. I think Moore's minimization, where we have like partitions and things like that. So what I'm doing is that I'm storing the partitions, and I'm storing mappings between partitions and states, and that helps me to sort of like apply some logic to find out to tell me what partition a set is in and all that good stuff. So this is what I have here, and this can actually be used in many places because as hash tables we're going to use them as maps. If you've programmed in Java or C++ or Python on any of those higher level programming languages, you have maps. The idea of maps where you have like a key and a value. So it's the same thing here. We have a key that points us to some particular value. And then these are like general purpose, hash tables. They are general purpose hash tables. We can store whatever we want to store in these particular hash tables. And then the key can be anything. It can be a string. It can be an int. It can be, a pointer. It can be anything. Same as the value. The value can be any of those, values I've mentioned, and many other values that we've not, discussed. So these are like general purpose, operators. And I also have like iterators. So iterators, again, if you've programmed in Java and have looked at, hash maps, all those containers. If you've looked at containers in a programming language like Java, or maybe C++, we have the idea of iterators. Okay, iterators are structures that help us, loop through the data stored in some particular container. In this particular case, the container is the hash table, and an iterator is a structure that helps us to loop through each particular item. So yep. So we also have like iterators for our sets. I think I have iterators for sets. Yeah. So this helps me to, write clean code, and it helps me like understand what is happening. Especially without these iterators, we'd have to like write, for loops, and if we're like writing for loops everywhere in our code, it sort of like messes up things, and it makes things, hard to follow and things like that. So yeah, so this helps us, hide all that messy logic. We'll still have to write for loops here and there, but then the iterators sort of like help us mask all that messy logic that we have. Apart from that, we have, I think I'm trying to, because, iterators are so useful, I'm trying to look for, a way to sort of like implement iterators, like generally implement them in C, for example, so that I can use them in many other places. because with the current implementation, for sets, I have like different iterators. And then for hash tables, I have like different iterators. And so this becomes, like very hard to follow, because if I like introduce another structure, I have to come up with an iterator that is adapted for that particular structure, right? Adapted to that particular structure. And that doesn't make, it makes it, hard to like implement, and if there are any changes and things like that, that is going to like cost us. We have to like, change the things here and there. But then if we implement them in one place, we can sort of like reutilize everything in different places. And then I have like my memory wrappers here, like the FA malloc, the FA colloc, FA realloc, FA free. Maybe later on we'll see how we can use arenas and all that good stuff for memory allocation and things like that. So yeah. And then we have like some IO functions for like serialization, input output. So we export our automated data to a dot file. This is what generates the the dot file that we have here, right? And yeah, and then we also have like many other functions, dot stream, where you can like print to the standard output. You can export the data to the standard output. You can export the data to any stream, right? Any stream that is of the file structure, right? And then we also have like a version for JSON, and these are still unimplemented, like reading from a dot file, reading the information from a dot file, reading the information from a JSON file, and sort of like coming up with the automaton. So it's a little bit complicated, and it's not very easy to do. So I'm trying to like give myself time to sort of like reason and think about how that is going to be done, especially how that is going to be done with minimal dependencies, with zero to like, I would say with close to zero dependencies or anything like that, because that is the goal. We don't want to, sort of like depend on other things. We want to write everything on our own, right? So iterators, memory, and these folders are still empty. So this is just me, thinking about the overall structure of the entire project. So we have like the push down automata, we have the I think the Turing machines, and many other interesting things. So this is where the logic is going to go. Like for now, we're just working on the FA file, and then I also have like FA debug. This is like for printing, for printing information about the automaton. What we could have done here is we could have like maybe defined a macro in fa.h that sort of like includes those functions, a macro that sort of like includes those functions when the particular macro is defined, or it's something like that. But then, like I said, this is a very long header file, and of course I'm trying to like decompose it and put things in different places just for readability, maintainability, and lookup and all that good stuff. So yep. And we have FA operations, which is not complete yet. I only have like functions. I think I have I have union, I have intersection, I have like minimizing, I have determinize, and I think concatenation. The others I'm still thinking about, whether we need these functions, or maybe we need to like remove them, and sort of like how we can implement all those functions. And then we have like the stack-based operations where we can like pass in, n automata and specify the flag and the mode, and then it will sort of like return results. It will give us the the results based on the flags and the mode. Now flags is what operation do we want to take? So is it the union? Is it the intersection? So if we have like automata in a stack, we can decide whether we want to take the union. We can decide whether we want to take the intersection. We can decide whether we want to take the difference, the concatenation, and many of those nice operation. and operations. And then we also, the mode is about the associativity. Are we going to be using, are we going to be considering left associativity, or are we going to be considering right associativity? And then we have like examples of what we mean by left associative and right associative. And using maybe the tree data structure, we'll try to look at how we can implement we can implement the composition in parallel. So these are like general purpose wrappers around the existing functions for computing the union, the intersection, the concatenation, and many other interesting functions. So we actually rely on variadics in C, if you know what that is. So that is the basic idea. So that's everything. I think that's everything. And then everything else is just C logic, and everything else is just API related code organization and coding best practices. That's everything. But then the idea here is to be able to come up with an automata simulation library, and we're going to come up with the graphical user interface for this particular that depends or heavily relies on this particular library to sort of like visualize everything. So I can actually, I think I can show you like how the visualization tool is going to look like, how the graphical user interface is going to look like, because I tried to I think we have to go with Excalidraw, I think. So this is the graphical user interface. So this is how it's going to look like. So let's see if we can sort of like get a hand on that. So let's see if we can minimize that. So I got, my inspiration from a tool known as Packet Tracer. So I got my inspiration from a tool known as Packet Tracer. So Packet Tracer is a tool that we use to like visualize computer networks, simulate computer networks, and sort of like tell what is happening. We can infer what is happening in a computer network from the simulations that we have here. So that's where I got my inspiration. So you can see that this is the graphical user interface we are trying to build. And this is like going to be our like main view. And then we have simulate, where we can like provide a string here in this particular input box. And then when we hit go, we can sort of like see how a particular string is accepted or rejected by the automaton. So this is the basic idea. And then so we can have like real-time simulations and all that good stuff. And so just like our Packet Tracer and things like that. And then here we have this window, this section here where we have like templates, different templates for Turing machines, different templates for DFAs, different templates for PDAs, different templates for NFAs, and many of those things. And then we have like the states. When we click on the states buttons, the states button, it gives us it gives us like tools. It gives us I would say controls. Okay, because we are talking about graphical user interfaces. It gives us controls for creating states, controls for creating starting states, controls for creating ending states, controls for creating many other things. So that is what we have here. Same thing, transitions. The transitions part gives us controls for creating. I think for creating transitions, right? And the alphabet gives us controls for creating symbols or for adding symbols. So that's what we have here. And then we have like a properties inspector just like in many other graphical user interfaces, we have like a properties inspector that tells us the color of each state, and then we are free to like change the color to match our preferences. And yeah, we can change the font size and many other things. So this is the properties inspector. And then we have like the file dialog, the edit dialog, the view dialog, and things like that. And then we have like different views. We can like see the table view of this same automaton that we are seeing here. And then we can like see the formal or mathematical view of this particular automaton that we have here. Then we can also see the maybe the JSON format or the dot format of the same automaton that we have here, right? So these are the different features and functionalities for the items in the menu bar. And we also have like these contextual menus, like what happens when you hover over a state, when you right click over a particular state, when you right click over a transition. So you get customized menus based on the object on which the right click is performed, and the styles and colors and everything. So this is, the basic design is done. So I actually prefer using Excalibur because there are better tools you can use to like come up with like graphical user interfaces, Figma and all those tools. But I don't want to be overwhelmed by the complexity and by their complexity, because things like colors and all that, and it's just like very complex for me. But it's doable, but it's like complex. But right, what I needed is sort of like visualize the controls, visualize the buttons, and the colors and everything can come in at the very end. Now I have like a solid picture of what we want to develop as as our graphical user interface for that is going to rely on the Fintom library. So at the moment, the two GitHub repositories are private. So I'm going to like make them public later on. If I sort of like have a stable first version, if I get the serialization, the stack-based operations, and the parallel processing, and maybe just operations on NFS, DFS, if I polish up all the functions, I'll be able to see if I can like make the repository public so that you guys can be able to contribute to this repository. Thank you guys for watching, and I'll see you in the next video.